for Lauren and for Hannah. Okay, related rates are when we're looking at something. This is sort of parametric, right? We have some function, and oops, I erased it. I didn't mean to do that. We have a function a, and a is actually a function of both x and y, and x and y are both functions of time. So x and y actually change with respect to time, and a is a function of x and y. Well, if a is a function of x and y, and x and y are both functions of t, then we can say that a changes with respect to time also, right? Because x and y are also changing. And so when we look at related rates, we're looking at how the rate of some function changes with respect to time, and it is actually a function of things that are also functions of time. This is very parametric. So let's go on to an example. So this actually represents the length, the distance between 2 points, right? Remember, that must look familiar, right? The distance, it's the Pythagorean theorem. So if we want to know, imagine that we have 2 points, and this represents, the distance between 2 points. And so and x and y are both changing, right? So how do we find the derivative of the distance with respect to time? Well, it's going to be the derivative with respect to time of d, and d happens to be x squared plus y squared raised to the 1/2. So we're going to take the derivative. We have to remember that x and y are both functions of time, okay? So this is going to be equal to, well, the 1/2 goes in front, it's definitely chain rule, times x squared plus y squared to the 1/2 minus 1, which is a negative 1/2, times, and now I have to take the derivative of x squared plus y squared. The derivative of x squared is 2x, but the derivative of x with respect to time is dx dt, plus the derivative of y squared is 2y, and the derivative of y with respect to time is dy dt. Now, the reason this is called related rates, and we could clean this up, is because the rate of big D, the rate of change of big D with respect to time, is directly related to the rate of how x changes and how y changes. Does that make sense? And so that's why it's called related rates, because rates are related to each other. And I'm going to do another example. I actually did this twice again over here. All right, so let's do this example. Assume that the radius of a sphere is a differentiable function of time, and let v be the volume. Find an equation that relates the change in the volume with respect to time and the change of the radius with respect to time. And this is a sort of a simple one. I'm moving this up a little bit because as the previous problem had x and y, there's only two. We had 3 rates that were related. Now we only have 2 rates that are related. So v is going to be the sphere, 4/3 pi r cubed, and we want to take the derivative of both sides with respect to time. The change in volume of the sphere with respect to time is equal to, well, 4 pi over 3 is our constant, times the derivative of r squared with respect to r is 2r, times the derivative of r with respect to t, which is dr dt. And what we have, we can certainly simplify this equation. Oh, I made a mistake, didn't I? The volume is cubed, right? So this is really 3, and that's squared. Okay, so the 3's cancel out, and we end up with 4 pi r squared dr dt. And so what we have is a relationship between 2 rates, and that's why they're called related rates. These 2 rates are related. Make sense? Okay, so let's try another one. I did this one. Assume that the radius and height of a cone are differentiable functions, and let v be the volume. Find an equation that relates both the rate of change of the volume, the rate of change of the radius, and the rate of change of the height. And of course, we remember from geometry, oops, that was supposed to be in sort of an ellipse, that a cone Who remembers the formula for the volume of a cone? Anybody? What's the volume of a cone? Do you remember I said you can put the cone into a base into a cylinder with the same size base, and it is what percent of it? It's a 1/3 actually. It's interesting. It's one third. 1/3 the volume of the cone. So it's 1/3 pi r squared, that's the base, times the height. So we want to relate the change in the volume, the rate of the volume change, the rate of the radius change, and the rate of the height change. So dv dt is equal to, what we have here is the product rule, don't we? Right? Yeah, let's pull the constant out. The constant is pi over 3. Now we have r squared h, right? So we have to take the derivative of r squared h with respect to r times the derivative of r with respect to t. And this is the product rule. Actually, let me back out of here. Let's just say it in terms of the product rule. It's the first times the derivative of the second plus the second times the derivative of the first, right? Because there's two functions and they're both functions of time. So it's r squared, the first, because here's the first, r squared, and the second is h. And the times the derivative of the second, dh dt, is the product rule, plus the second, which is h, times the derivative of the first, which is 2r dr dt, right? So I'll put the 2 here, I'll put the r here, dr dt. Does that make sense? This is the change, this is the rate of the volume, and it is related to the rate of the change of the height and the rate of the change of the radius. So the rate of the change of the volume is related to two other rates. Does that make sense? I think I have another one. Let's see. Oh, I did this one out. Nope, that was the last one. Okay, so let's do some more practice problems. I'm going to stop this. I have to stop this because if it's too long, I can't save it.